Well, good morning, everyone. Let's start with a webinar about SQL Server 2016. It's a webinar about a few of the new features of SQL Server 2016. Now, this session is going to go about the big data parts and about the new features which are included in CDP 2.3. What is the new challenges of our era is actually to manage our data. Actually, the challenges of this era is to manage our data. So this session is about the new features in SQL Server that are giving us more possibility to manage our data and the expansion of the data. What does this mean? Well, I put this in figures. In SQL Server, actually the digital universe in 2013 was 4.4 trillion gigabyte. This is roughly 3 zettabytes. Of all that data, only 22% is actually useful. That means that there is a lot of noise in the data, and people will have challenges to extract the useful data from the noise or the rubbish in the data. Now, let's expand this to 2020. Well, in 2020, the data will be, the digital data universe is estimated to be 35.2 zettabytes or 44 trillion gigabytes. This is important because the usefulness of the data will also increase to 37%. So not only the data has become 10 times bigger, but the usefulness of the data is also more important. This gives us a few very interesting issues actually. One of these issues is that it becomes more and more difficult to manage and to actually control our data flows. I'll give a few examples. For example, to back up your data. Let's say most of us are still hanging on to their daily backup. And when your data becomes 10 times bigger, you will still have enough maintenance window to take a backup of all your data. Let's say if you have now a 20 terabyte database, backing that up will take a lot of time. So you will probably have to fall back to file group backups and other technologies. Another very important issue that is often forgotten is that the time needed to recover your database is also increasing. So it's not because you have a backup that you will be able to recover your database in time. We all have RTOs and RPOs to live to, and if the time needed to recover your database becomes bigger than your available window to restore, you have another problem. That's why I added the little image of our disaster recovery plan just exploded. What does this mean? This means if we have to recover huge data sets and that takes like 20 hours, well, people aren't going to be happy. Also, server maintenance, big servers need more maintenance. So it takes longer and longer to perform all our maintenance on our servers and on our recoveries. This also means that we become less and less involved in actually testing our recovery plans. So we end up with having a backup and restore plan that takes too long to recover and we won't even know. So that are the challenges for the following years. So what are we going to see today? Well, in SQL Server, they've added extra features that will allow us to scale in our tier 1. Today we're going to look into operational analytics, the in-memory enhancements, the column store enhancements, and I see that my cross moved, the native JSON support and what that does mean for SQL Server. So let's look into what that means. Now, actually, in our term, operational means the OLTP loads. OLTP loads is mission critical, should have no downtime, needs high availability, We don't want any negative impact on revenue, and most of them have a high transaction throughput. Now, what is analytics? Analytics is actually investigating our past data, like operational or social media data, to identify potential trends. Analyzing the effects of some decisions or events, such as an ad campaign or a social media campaign, and look into the past and into the current data, what are the effects of these actions or events. Now, like you see, these data is not really compatible, because an OLTP data is small, high transactional throughput, and has low latency, while for the analytics, we want to actually cross over large data sets. What does operational analytics means is combining those two technologies together and make a big improvement. What did Microsoft add in SQL Server 2016 is in the column store is actually added into the in-memory tables. The rows, the tail that is in the column store will stay in an in-memory OLTP table. It's a small chunk actually. And there is no column store index overhead when the tuple mover needs to move it from the row store into the column store. This is a big improvement compared with the 2014 column store. And there is also another big change. In the 2014 column store, the tuple mover will only move the data after a chunk of 1 million rows that is not changed. In SQL 2016, this is added with not changed in the last 1 hour. So that means that there is a faster flow of the movement from the row store into the column store. This is a very important change actually. The data warehouse queries are now able to run in an in-memory OLTP workload without any application change. So these operations should have minimal impact on your OLTP workload because they are actually in a separated memory store and they are not running directly on the OLTP system. Of course, this would require more memory for your server, but that means that you have a separated memory environment where your analytic queries can run on the same system as your OLTP system. The best performance and scalability will still be when you actually can separate them though. What is the goal of this? The goal is actually able to offload analytic workload to a readable secondary where you then can use your memory pool of that readable secondary, which is not really used because in the readable secondary you will only need the memory to keep the system in sync. But if you have then the in-memory OLTP system for your column store, your analytical queries will run much faster. This is a very, very big change, which has a huge impact in the way how we can do real-time analytics. For that, there are some very important in-memory changes to the Hackathon engine. One of the things that is important for the change in the Hackathon engine is that we can now change the bucket count. In 2014, when we misjudged the bucket count, we had to recreate the table and do an actual data movement. Now we can change the bucket count with an alter index statement. This does mean that we can alter operations in in-memory tables in SQL 2016, something which was not possible in SQL 2004. There are some drawbacks though. If we want to do alter statements, we actually place a full lock on the in-memory object, which means that we will have to hold the workload. So while we can alter the schemas and the properties of an in-memory table, we do need to do this in maintenance time though. Any user or transaction that is started before the alter statement will have to actually will make the alter statement fail. So we actually really have to shut down any workload on that system. The alter table syntax is then used for making changes to the table schema as well as for adding, deleting, and rebuilding indexes. So this is important. This means that the indexes are considered part of the table definition. They cannot be seen as different objects. The alter table drop alter index is supported, but only for memory optimized tables. In that, that combination. So it's alter table add index or alter table drop index. So it's a slightly different syntax compared to your regular index maintenance. The normal alter index without alter table is not supported for the in-memory tables. Improvements are done so that we can enable scaling to larger databases and higher throughput. And one of the technologies that is now embedded is that we can also have MARS support on in-memory tables. Also, it will scale much higher. In the SQL 2014, there were a lot of limitations on in-memory tables, and which of some very important ones are now finally resolved. What do I mean? There are big changes to the create procedure transact SQL coverage. We can now actually drop a procedure and alter a procedure. This is very important because these are natively compiled stored procedures. We can now finally use schema binding. We can finally use table valued parameters. And we can actually grant and deny permissions on tables and stored procedures. This is very specifically to the Hackathon engine, of course. We can also use grant and deny permissions on tables and procedures. And also this is a very big change. Now we're going to go some even more important changes. We can now finally nest natively compiled stored procedures. With SQL 2014, we had to have all the stored procedures had to be self-contained, which means that we could not call another stored procedure. This limitation is now finally removed so that we can now nest them. There's one thing to keep in mind though, you can only nest natively compiled stored procedures, so you cannot nest non-natively compiled stored procedures. Another very important change is that we can now finally use outer joins and inner joins in our select statements. There is a limitation though, that if you use joins, that for the best performance you best join in-memory tables with in-memory tables. If you do not do that, then you will have a drop in performance. Other very important operations are not, or, and the in operators. We can now also use update and delete statements in the where clause, having clause, and join conditions. This support is not extended to between, unfortunately. Also, union all and union are finally supported, and the select distinct clause is supported. So this means that we no longer have to completely rewrite the in-memory tables, so it will be a better fit. Of course, you see a lot of statements being added for the column store, because the column store is actually optimized for aggregate queries. And in the original Hackathon engine, we did not have the possibility to aggregate. So it's really important that this has been added. I made a night comparison between SQL 2014 and SQL 2012, where you can see the improvements in the in-memory tables. So which is important is that we now have additional B-tree indexes for more efficiency on the short-range searches. We can have primary keys and foreign key constraints, also extremely important for the clustered column store index. For the updatable non-clustered index, we are now able to mix OLTP and analytics workload, and we have the ability to create filtered non-clustered indexes. You cannot enlarge the table, but you can change the bucket count so that the maximum size of the in-memory table has been enlarged, but you will have to make an alter statement, an alter table, alter index statement to change the bucket count so that it is able to contain more rows. So you see, we have now a more flexible, more usable in-memory table in SQL 2014, which allows us for a bigger usage. Also, the reports get to advise you which tables are better moved to Hackathon tables has been greatly improved, so that you can make a good decision which tables should be moved to the new environment. Then we're coming to another topic which I really love that they finally put it into SQL Server 2016, and that is Polybase. Polybase is an existing Microsoft tool that was actually introduced in the PDW, and allows us to actually fire SQL queries against large non-relational databases, for example, like stored with Hadoop. Like I said, previously Polybase was only integrated with SQL Server Parallel Data Warehouse, and this allows us for a scalable, cost-effective way to store large amount of data and and the Polybase is actually a SQL connector to Hadoop and also to Azure Blob Storage. This feature is variant for data processing, and it involves, for example, like when is this interesting? Like when you have a lot of measurements, you have a lot of text messages, documents that you want to actually query with SQL Server. Then you can extend these objects into your Hadoop or Azure Blob Storage, and then query those databases, those data directly from SQL Server using your relational SQL interface. What is important is that these text objects can be queried like they were database tables. So it makes it easier to access your Hadoop environment. So what does Polybase actually do? Well, Polybase allows you to use these SQL statements to access your data stored in Hadoop or the Azure Blob Storage and actually query it like it were ad hoc data sets. It also lets you query semi-structured data and join your results with your relational data set that are already stored in SQL Server. So Polybase is actually optimized for data warehousing workloads, and it's intended for analytical query scenarios. Polybase will then address one of the most important customer pain points in data warehousing, is that actually it's very difficult to access distributed data sets without having very difficult and very extensive ETL sets. Now you can just post your data on your Hadoop cluster and directly query them like they were tables. Because with the increased volumes of unstructured or semi-structured data sets, we are storing the sets in the most cost-efficient way as possible. Now, we could just store them on a file share and load them in the database every time, or we can just leave them in the Hadoop store and then use the Polybase tables to query them directly. What is very important, however, is that if you would just put them on the Hadoop and you would not have Polybase, it becomes more and more difficult to actually access these data sets. It would require new platform skills, it would require new application, it would require new insights. Polybase will solve this issue for you, because actually by creating the extended table, your Hadoop blob store becomes a table just like any other one, and you just can access them like any first-class SQL object. You can see it like a linked server, but where the data actually resides in your Hadoop cluster. This is a very powerful tool because it enables you to, for example, store a large data sets in the Azure Blob Store and query them just like they were on premise. This brings me to another very, very nice and powerful feature of SQL 2016 is that we can use stretched databases. A stretched database is a promise to have cloud at your service if you need it. For what it will allow you to do is create a table that contains a small amount of hot data which is stored locally that your users constantly need to query, and then there is that archive part that becomes bigger and bigger, but you can't delete because there are regulations or because your users say they still need all the data. So what do you want to do with this? We all know that server storage is very expensive and cloud storage is, well, let's say, a lot cheaper. So when we enable stretched database, it will create a second database hosted in Azure. You should see it as an Azure database. And then when you mark a table as stretched, SQL Server will automatically start moving its data into the cloud. It does this by, like say, bit by bit, small, easy, and by that way it will start to archive your data into the Azure database. This means that SQL Server will decide which data is hot and which data will be considered archivable. The archive mode, unfortunately not released yet, will use a where clause to determine which rows to archive. In the current CTP, it will actually try to stretch the complete data set. Whenever the new feature will be completely available, I'm sure it will tell you. Common scenarios are, for example, you have a lot of data, and let's say your users are only interested in the current year, but you have like 10 years of data in your table. For SQL Server, this would mean that this current year will still be on premise, will be easily accessible, but the other part will like be a giant partition, will be placed into the cloud. So for SQL Server, actually the stretch table will be considered like any normal table. The query execution engine will automatically take care of the distribution of the query between the local and your Azure-based server. And that also means that you can enable stretch on a database without any changes for the application. So it will be completely transparent. Backup and restore will need to change. Normal backups will only include the local host data. This is very important. A full backup included data locations in the stretch database will require a different procedure. There are some limitations though, and let's say some column types are not supported. For example, file stream, timestamp, SQL variant XML. This is very unfortunate if you ask me. The geodata and hierarched data types are, for example, are not supported. This also means some specific indexes like XML indexes and full text indexes are not supported. And what I do find very unfortunate is that the clustered column store index is not supported though. There is another drawback is that indexed views referencing this table are not supported as well. What actually happens? After you enable stretch database for a local server, an instance or a database, or at least one table, it will silently begin to migrate your historical data to an Azure SQL database. You can pause the data migrations if you have issues with your available network bandwidth. You can actually say we will only allow it to run during non-office hours. So you can actually say we pause it during office hours and we let it work during non-office hours. Stretch database will ensure that no data is lost if a failure occurs during migrations, and it has a retry logic to handle the connection issues that might occur during migration. And then DMV will provide you the status of the migration, and so you can see how much of the data is actually migrated and actually in what state your server, your data table is in at this moment. You don't have to change any queries or client apps. You will have to change your backups though. There is an important fact that if you would make a large query including the whole set, you will encounter some latency. The other important thing is that as long as you're not using the stretch table, you will only have to pay for the storage. When you will have to pay for the stretch database is when you actually execute a query on it. Then you will have to pay from some CPU cycles and for the download itself. But for just storing it, the cost will be absolutely minimal. So I have a nice schema how it actually tickles your data movement. So when are stretch databases interesting? Let's say if you need a lot of data and you have to keep it for a long time due to legal implementations. For example, I know there is some data that you have to retain for 10 years. If because of the data explosion that we have now, retaining this data for 10 years will be immensely expensive. So by using stretch database, we can keep it in the database without having to archive it, and it will still be available for your end users to use and to query. Another very important thing, which is not mentioned on the slides, is that in SQL 2016, we have per default, we have encryption on the complete system. So even your stretch database will also be encrypted. So what kind of databases and tables are actually candidates for a stretch database? Well, stretch databases targets transactional databases. It's for the moment, it's not intended for analytical databases, which have the burden of having a lot of historical data. Typically, those will be stored in a small number of tables. For example, we have our measurement table containing like 30% of your complete database. Why is it 30%? Because it contains data of 5 years. Well, that would be an ideal candidate for using stretch databases. Typically, those tables can contain millions or even billions of rows. It's difficult to maintain and to keep them on site. In that case, the stretch database will keep your system and fast, because it will only need its resources, its local resources, when using the local storage. When extending your query to the stretch database, the query will actually be executed on the Azure part, and it will not have to return the whole data set. It will only return the conditions that are specified in your where clause. Okay, now this concludes my small introduction to some new features in SQL 2016.